Okay, so let's get started. We're going to be taking a look in this training module at understanding the differences between Lambda, air fuel, and stoichiometric. Now, these all are related to each other, but there's a lot of confusion. People start calibrating and tuning with something like a Gen 3 engine control module, and they're not coming from, let's say, they working with standalone tuning and they're coming into the Ford programming language. Things can get a little bit confusing, so this tutorial hopefully makes sense of what each of these three things represent and why we need to know the differences between them. We're going to be using our VCM editor software here, opening up a stock calibration file, taking a look at a few things in the programming so we make better sense of this. We're also going to be then using our Excel spreadsheet calculator. I have some things to help us do a translation, understanding the fuel and airflow model, understanding the differences between the fuel Stoich and Lambda, and then also translating Lambda to petrol air fuel scale. So you may be familiar with, if you've done tuning on other platforms, let's say you're using a standalone system, you have a wideband installed with the standalone system, or you're looking at a wideband gauge from a modified car, you know the wideband's going to read typically between 10 to 20 to 1 air fuel. That's a petrol air fuel scale. And we'll find natively widebands will always read in units of Lambda, but convert to the petrol air fuel, what you actually display on the gauge. So we're going to see how that translation works. That'll hopefully clear up some of the confusion here that people get as they start calibrating and tuning and working with OEM ECMs for programming. So let's jump in here and let's open up a stock equivalent file so we can start to take a look at a few things, and then we'll move into our Excel spreadsheet to do some demonstrations, and it should clear up any confusion that you may have. So the very first thing we'll do here is go up to File, Open, and we're going to move in to the course training folder here, so HBT Gen 3 Coyote, and we're going to go in here to our sample calibration files, and any of the stock equivalent files here will work. Technically, any file will work. I'm going to open up that same file I've been working with through the whole training course so far, so 2019 Mustang GT manual stock. Again, any stock file or your equivalent file will work as well. Looking at this, if we go in here to the engine tab, and we go here from General, and we move over here to Fuel, and we go over here to General, we're going to find the first thing I want to point out is going to be our Stoich AFR. This is going to represent 14.08 is 10% ethanol in our fuel system. So it's 10% ethanol blend, 90% petrol. So this Stoich AFR is very important. That needs to be accurate. If you had non-ethanol fuel available to you, you'd program this at 14.68. If you have 10% blended ethanol in your fuel system, you'd program it at 14.08. If you have, let's say, 85% ethanol and you're not doing a flex fuel tune, then you would enter this Stoich AFR representative of whatever that Stoich to ethanol blend percent is going to be. We'll be able to use our Excel calculator to figure that out to be able to program it. But this is super important. This acts as a overall global scaler to your injector pulse width conversion. So we know the engine control module, it's going to be looking at the airflow. It's going to look at what we have for a desired program, Lambda or target air fuel. It's then going to calculate a fuel mass, convert that into an injector pulse width, knowing our injector data information here. The Stoich value here will alter that target air fuel that we calculate, which will then alter the injector pulse width and alter the fueling to the engine. So the Stoich AFR here is what we use to correct our fueling based on the amount of ethanol to petrol blend we have in our fuel system. Again, this will make more sense here in a little bit. We also have, if we move over here to open loop base, we have some tables here, and we want to take a look at, if we pop in here to our fuel base cold, this table here is used for the engine fires off cold. It references a desired target Lambda amount. We can see the units here in Lambda. So 1.0 Lambda, that's known as stoichiometric. That's what we want to run our engine at idle, part throttle cruise. We run a richer mixture. We move into optimal power under higher load, higher throttle. Let's get more power out of the engine and doing it safely. But we find that this table here is going to be calling out in units of Lambda. If we move over here to power enrich, let's close this table out, and we take a look, we're going to find that the power enrich, we have our watt Lambda values. This is calling out what the desired watt Lambda is going to be under full throttle conditions. So we see here, again, units are in Lambda, and we find that the values are lower. It's not 1.0, it's something like 0.85 to 0.82 Lambda. So the lower the value, the richer the mixture that we're trying to call out. The higher the value from 1.0, the leaner the mixture. So depending on where we're operating at, we may be calling out above 1.0 Lambda, not typically, or if we're under higher load, or we have catalyst protection in place, so we need to cool down the cats. We command a richer target, Lambda, and this is where it all happens from. And this is what Ford uses for its programming. But let's make better sense of this. Let's understand what's going on here. So if we pop into our Excel spreadsheet and we move to our page or tab here called Stoich, we have a couple different things to talk about here to understand kind of the different aspects or topics that I just pointed out. We have our stoichiometric ratio, we have our Lambda values. How does this all tie in? How does this make sense? Let's first talk about our overall airflow model and how we translate airflow into fueling to the engine. And we find that we use a mass airflow sensor on a Mustang or the speed density operation on an F-150. We register the amount of air mass that's coming into the engine. We can actually take a look at a logging PID for Mustangs based on the mass airflow sensor. We can actually see what the grams per second of air mass registration is going to be. So if we pop in here and just look at a VCM scanner here for just a second, I have a data log open. There's a bunch of data logs you can open up, sample data logs from our training course folder. I have a wide open throttle, looks like our MAF tuning log here, MAF tuning 3 from our training course folder. We can take a look. We're going to find, let's just say here at idle, I'm approximately idle about 900,000 RPM. We're going to find that the mass airflow sensor is showing 8.2 grams per second of airflow registered. So this is what it's showing is coming into the engine at this particular point in time.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.